These trainings are at no cost, thanks to the sponsors of Energize Connecticut, and are part of a partnership with Connecticut Passive House and Build Green CT. And today's training will be recorded and made available in the Build Green CT video library afterwards. A reminder that as part of this training workforce development initiative, we offer 75% cost reimbursement for individuals pursuing either Phius or PHI professional accreditation. This includes the cost of the trainings and the exam, and once you become certified, we'll work with you to process the 75% reimbursement. So if you have any questions about that, please reach out to us at the email address shown here on the slide. Um, Lauren, if you can go to the next one. In addition to the no-cost educational training series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to go all electric with their residential buildings or pursue Passive House certification in multifamily projects with 5 units or more. The Passive House incentive design includes pre-construction incentives for feasibility studies and energy modeling, and post-construction incentives up to 100% of the cost of full Passive House certification, capped at $1,500 per dwelling unit. Next one, Lauren. And the all-electric and high-performance certification bonus incentives are available for both single-family and multifamily buildings. There are 3 incentive tiers that projects can qualify for with different performance criteria for each, and incentives range from $1,500 per multifamily unit to $12,500 for single-family homes, in addition to adder incentives for high-performance heat pump equipment and certifications such as Energy Star, LEED, and DOE Efficient New Homes Program. Our goal is ultimately for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you're interested in learning more, please visit our website or contact us at the number shown on the slide. So for today's session, please feel free to use the Zoom Q&A feature to submit questions to our presenters, and we will relay them. And as Sarah said, today's session is approved for AIA and Phius credits. We'll be following up with you after the session if you're interested in those. And with that, I'll introduce today's speaker. Lauren Gunther is the Director of Sustainability with DeMello Schaefer, a registered architect and CPHC. And Kristen McDougall is a project manager with DeMello Schaefer and also a registered architect and CPHC. So, Kristen, Lauren, with that, I'll let you take it away.
Great. Thank you so much. Hi, everyone. We are so excited to be here and present to you today, Pushing Boundaries, Applying Phius CORE to Internal Load-Dominated Buildings. We'd also like to thank Build Green Connecticut and Energize Connecticut for organizing this webinar. So as Keegan mentioned, I'm Lauren Gunter, Director of Sustainability at DeMello Schaefer, and joining me is Kristen McDougall, Project Manager of this project. We're both part of the core and shell architecture team for this medical office building. So I'm not going to go into great detail on the learning objectives, but what we want to emphasize is that you come away with an understanding of how to apply passive house principles to large commercial buildings and to know that it is doable and you can work with Phius to get there. So here's the agenda. We're going to start with policy as a driver, the Massachusetts Energy Codes. That's really a huge driver and how we landed with passive house for this building typology. Then we'll go into envelope optimization, the passive house process, mechanical considerations, meeting source energy limit, and then we'll close out with a summary. So here's the project. It's a 110,000 square foot medical office building. We are under the new Massachusetts Stretch Energy Code, which I'll clarify in a moment in terms of what that means. The building will be 100% electrified for heating and cooling and domestic hot water, and is considered net zero ready because of that electrification and because of the significant reduction in energy use. And this building is the first ambulatory care facility to pursue passive house certification in the nation. And we also just received design certification. So we're really excited about that. And the project is also pursuing LEED. So we'll now transition to a brief overview of the relevant policies. I first want to start with the Connecticut decarbonization timeline, which was updated in 2025. This timeline is very similar to Massachusetts, as you'll see shortly. And shows the target of 45% reduction in greenhouse gas emissions by 2030, 70% reduction by 2040, and then net zero or 100% reduction by 2050. So, and then here is the Massachusetts decarbonization timeline, which, as you can see, very similar. And really, what drove this was the Climate Act of 2021, really that set the stage for our new Massachusetts energy codes. And it's has very similar targets, 50% by 2030, 75% reduction by 2040, and then net zero or 100% reduction by 2050. So I'm not going to go into super detail on our Massachusetts energy code. As Kristen knows, I could probably talk an entire day about our energy code. It's got many layers to it, and many components, and which is why we've mapped out these helpful decision trees to really clarify what are the triggers for our particular building type. And for ours, which is considered a large, low ventilation office building, we had two pathways. One is the targeted performance or the thermal energy demand intensity pathway, which basically puts limits on heating and cooling demand, very similar to Passive House. But it was a new pathway that came out in 2023 when we started working on this project. And so we decided that with the other optional pathway, Passive House, that this would be a more tried and true pathway of getting to the requirements. So this is a live map that Demeller Schaefer has created and is located on our website showing the energy code effective dates for each town or city. We have three tiers of energy codes, the base energy code, and then the stretch code, which is available by town or city vote, and then the specialized opt-in code, which is also available by town or city vote. So the light green represents the base energy code, which is only 49 communities out of 356. And then the medium green are the stretch code communities, which is 242 communities. And that code is much stricter than our base code. And then 60 communities have adopted the specialized opt-in code, our strictest energy code, and those are indicated by dark green and purple. The purple represents the fossil fuel free program, in addition to our specialized opt-in code, which eliminates fossil fuels in 10 communities. And we track this really closely because we work in so many different communities in Massachusetts, and this has become a helpful tool for beginning a project. We're also, in addition to the energy code adoption across the state, we're tracking the number of passive house projects each year. So you can already see a noticeable uptick in projects starting in 2023, which coincides with the rollout of the new Massachusetts Energy Code. And this really demonstrates the power of policy. Really want to shout out to the Massachusetts Department of Energy Resources and all the great work that they've been doing, because it was really significant in terms of policy in all those dark green municipalities. Passive house is required for multifamily greater than 12,000 square feet. So that is really what has been driving this passive house. And so then finally you see that there's been a significant progress with the number of registered projects at the end here with the pink color. So now I'll pass it over to Kristen to talk about envelopes.
Thank you, Lauren. I'll start by talking a little bit about how we approached the envelope design for best Phius results. Much of what we did for the envelope optimization for this medical office building is similar to what you might do for more typical residential passive house projects. However, there are a few differences we'd like to highlight. And the first thing we looked at was getting the window to wall ratio correct. So from the outset, we didn't approach this like a traditional office building that is predominantly glass. When we started thinking about envelope optimization, we knew that we wanted to keep our window to wall ratio under 30%, but we didn't necessarily want the building to look like it was under 30%. So our first step was to concentrate the glazing where you get the most bang for your buck. And for us, that meant animating the ground level and entry areas. Next, we chose to use insulated metal panel with a backup wall above and below our windows, rather than using spandrel glass, which would have significantly brought down our envelope performance. By recessing the surface above and below the window, that insulated backup wall, so that it's more in plane with the window than the brick, you can fool the eye into thinking the punched window opening area is greater than it actually is. So looking at this front facade, it looks like we have about 43% windows, when in reality, it's only 25%. Pretty stark difference. Zooming in now on that sill detail, you can see how we divorced the metal panel from the brick beyond and pushed it as close as possible to the plane of the window in order for them to read as a unit. This helps with thermal performance. So ideally, the window should stay in line with your exterior insulation for best thermal performance. And you want all of those isotherm lines to be as straight as possible. However, this arrangement can lead to challenges with supporting the window. How do you support a window that's completely off the stud wall, but still manage the thermal bridging? We originally detailed this with a thermal buck product, but the client was hesitant to use something so different from what they are used to using in commercial architecture. So we ended up using a fiberglass extrusion around the window instead. And because it was fiberglass rather than metal, it helped mitigate the thermal bridging.
Oop, sorry.
No worries. So here's an axon of that same detail. And a couple of other things that you'll notice here. We've got our air barrier system that is shown in this kind of grayish purple, and also a detail membrane highlighted here in kind of a bright blue. That's just a peel and stick membrane. And that laps over our AVB and wraps the exterior insulation. We did that to tie the window into the air barrier system. And we're not showing the exterior insulation here, just to note for clarity purposes. The other thing we'd like to highlight is that the Phius system, as opposed to the Passive House Institute system from Germany, allows a little more flexibility in how you balance the thermal comfort. So we were surprised to be able to get away with only double glazing here, which is not typical for passive house projects in Massachusetts. But it is possible for buildings that are internal load dominated rather than skin dominated. And Lauren will get into how we were able to do that a little bit more in the next section. Now for real life, the building is currently in construction and they're just about to get the building buttoned up. They have been installing windows recently. You can see here the air barrier, which is that grayish purple surface over the whole wall. And then the green girt is the window surround and also the detail membrane there in blue. The picture to the right shows the mock-up we did for air leakage testing. And rather than building a chamber behind the window, which is pretty common for air testing windows, they were able to create a cavity here with plastic, just taping off plastic in front of the window and taping it to the detail membrane. And they were able to insert the hose there to do the pressurization tests. So I noted above that we were able to use double glazing instead of triple glazing for our windows. And we looked at the cost difference between double glazed and triple glazed. There's good and bad news here. So whereas a few years ago, you might have been looking at maybe a $500,000 premium for triple glazed windows, the price difference has gone down significantly due to the sharp increase in demand for triple glazing, which I think is probably due to the Phius effect, or definitely at least the new energy code effects. So funny story, we specified double glazing for this product, but the contractor actually submitted on triple glazing, which is, I think they just assumed, oh, passive house, we need triple glazing. And then when we asked for the credit, they only quoted us 135,000 in savings for the change. So, assuming they give us the actual price, the cost savings was not as robust as we had expected. But the good news is that the premium for triple glazed is much less than it used to be. So if you do need it, it's not such a hit to your project. We'd love feedback if any of you have seen the same thing with the cost of triple glazing. The other benefit to using double glazed windows is that this double glazed aluminum window has about 30% less embodied carbon than a triple glazed window. And now I'll pass it back to Lauren to discuss what we have discovered about the passive house design process for commercial buildings.
Thanks, Kristen. And now I'll go into more detail on that process. So here we're looking at the 5 main principles of a passive house. These are comprised of the following: that continuous insulation, what I like to equate to is like your heavy Canadian goose jacket. Um, and then we're looking to minimize thermal bridging. So really looking to minimize the amount of heat transfer from the inside to the outside or the outside to the inside. Then we have the airtight envelope. Again, minimizing transfer. Uh, and then balanced ventilation with heat recovery, really important for passive house projects and high performance projects in general, where we're recovering that waste heat from the ventilation system. And then finally, optimal solar orientation. So thinking about how the building is oriented and that window to wall ratio and minimizing heat gain in the summertime for a building like this. So the end product is an energy efficient, healthy, and resilient building. So here is our typical timeline for a passive house project. Starting with a Phius feasibility analysis and schematic design, we then build on that feasibility with model updates and 100% DD and 50% CD. Then we start the design certification submission process during construction documents, where we start to submit documents for the design or pre-certification with Phius. Then we aim to receive design certification before or at the start of construction. And then as construction evolves, we do extensive testing such as blower door testing, as well as duct leakage testing and balancing. And all of those testing results, as well as an updated model, gets submitted back to Phius. And then upon passing and submitting all those results for review, we receive final certification. However, this project ran on 2 separate timelines with 2 different architects, so the timeline was not quite typical. The top is the core and shell timeline that Kristen and I were a part of. The bottom is the medical office fit out timeline. And the 2 separate timelines presented challenges to the project. 50% CD would normally be a major review milestone, but when we were at that point in the process, the tenant fit out was only at the SD stage. So at this very early stage of fit out design, we were provided with very limited information on the interior, which makes it difficult for the passive house team to build an accurate energy model. So we'll go through that process now. So passive house models rely on detailed inputs of the internal building conditions. Early in the core and shell design, much of this information just wasn't available. We had very limited drawings. These inputs matter because internal loads directly affect envelope requirements, and which is the core and shell architect, we're responsible for the envelope. So the project includes very high energy medical equipment, such as an MRI or CAT scan, generating significant internal heat gains. And high internal heat gains allow for lower insulation levels without compromising performance. Meanwhile, the core and shell team needed early guidance on insulation and window specs. So over insulating would have increased cooling loads, costs, and embodied carbon. So we really, when it comes down to all of it, the bottom line is that we needed to understand the building program early much before things were really detailed in drawings in order to make the right envelope decisions. So in terms of the medical office program, it is very diverse. There's urgent care, labs, exam rooms, scanning, offices, and a pharmacy. We didn't have layouts, but we did have written program for space counts and sizes. So the Passive House consultant, Stephen Winter Associates, investigated quite in detail the working requirements for each of these spaces early on. So they looked at things like lighting, ventilation, usage, and anticipated plug loads. They also reviewed scanning equipment to estimate its energy impacts. So all of this was compiled and input into the WIFI passive energy model. And then doing all this investigation work was just extremely important. The mechanical team's early ventilation rates prior to really being fully engaged on the project were about 30% higher than Stephen Winter's calculations. And really, to no one's fault, it can be typical in earlier stages to overestimate um, uh, aspects until the design is further refined. But because of Stephen Winter's analysis, they were able to show that those ventilation rates were likely too high. And the mechanical engineer aligned on the lower ventilation values. And so if we had used the higher ventilation rates, the added energy use and heat loss would have forced trade-offs, meaning we likely would have had to upgrade to triple glazing instead of using double glazing. So this is why it was so critical for us. So the passive house model requires all internal electrical loads to be calculated. These loads are limited by a source energy cap, and source energy takes into account the energy a building uses plus the energy needed to transfer the electricity to our building. So and the losses and Kristen will go into that in later on in another section. So for the residential pathway, the source energy cap is based off the number of occupants. Whereas under the commercial pathway, this source energy cap is limited to 24.5 kb2s per square foot per year. So for the commercial pathway, the loads are split into two types. We have internal loads, which are your lighting, your fans, your elevators, appliances, office computers. Whereas process loads, these are the unique loads associated with the commercial process of the building. So in this project, process loads include medical equipment, such as an MRI, X-ray, CAT scanner, and exam room computers. So the key point to all of this, though, is the medical office process loads are allowed to raise the source energy limit. So the building isn't penalized for its function. It's key to discuss this early with Phius so that there's an agreement on what qualifies as a process load. For instance, office computers are considered an internal load, whereas an exam room computers are considered a process load. So while we're not penalized for source energy based on the process loads, they're still accounted for in the internal heat gains, which is a driver for our envelope. So the two bars here show a comparison between the standard internal equipment load, such as that lighting, the fans, office computers, and then the process load, which is that large medical equipment, such as the MRI. You can see that the loads account for a much higher amount of the building's energy. Significant. This is due to the large medical equipment, which you can see broken out here. And then again, to reiterate, we weren't penalized for these large process loads. So we're only then looking at the source energy related to the internal equipment loads. As I mentioned earlier, these internal loads give off heat, which we refer to as internal heat gains. To quantify these loads, I'm going to compare three passive house projects in Massachusetts. So a single family has an internal heat gain of 0.6 to 1 BTUs per hour per square foot, whereas a multifamily is more condensed, has more people, more appliances, has a higher internal heat gain of 1.2. Whereas a medical office building is over double this with 2.5 BTUs per hour per square foot. This large increase is due to the medical and office equipment. So higher internal heat gains mean you can reduce envelope insulation without compromising performance because you have more people and more equipment to generate that heat. So again, we're comparing three passive house types in Massachusetts, that single family, multifamily, and medical office. Single family homes are skin load dominated, which means they are envelope driven. Heat loss through the walls and windows is the main factor in driving total energy use for this building. And that also means that it requires more insulation. So you can see that the wall has between R35 and R40. Whereas a medical office building are internal load driven, equipment activity generate a lot of that heat. That heat helps warm the building, and then it allows for lower insulation levels, such as an R24 for the walls. And it also allows us to do a really high performing double glazed window, which is a 0.24 compared to a 0.15 triple glaze for a single family home. So understanding internal heat gains early let us really avoid over designing the envelope. And the result is that our envelope is very close to stretch code levels, except for the tighter air tightness. And the occupancy number and schedules are important to know because it influences the amount of energy the building is using. So depending on the function of a commercial building, there can be large portions of time where the building is unoccupied. So we needed to understand these utilization patterns for the staff and patients. How many days a week they're expected to be in the building, how many hours a day or holidays off. This graph here showed a 24-hour period. You can see that the building occupancy on Monday to Friday in blue, which is from 7 a.m. to 6 p.m., and is the standard working hours for this building. The building is then practically empty after the working day. And then we can also see there is a presence in the building on Saturdays, seen in red, but this drops on Sundays, which is seen in green. So the current medical office program is situated over 3 floors, with the fourth floor being unoccupied, and the fifth floor is a mechanical penthouse. We discussed the vacant space on the fourth floor with Phius early in design, and it was agreed that we would duplicate the layout and the internal loads of the third floor so that the whole building could be modeled and certified under Phius. The ground floor includes urgent care, which is open Monday to Saturday. The second and third floors and the lab space on the ground floor are open Monday to Friday. This information was important to determine not only for the Phius model, but because it allowed us to make operational adjustments to the mechanical systems, which reduced overall building energy consumptions and allowed the building to meet the Phius thresholds. So I'll now pass you back over to Kristen, and she's going to discuss these mechanical systems.
Thanks, Lauren. I'll be playing mechanical engineer here to describe our mechanical systems and how they impacted our passive house performance. So please bear with me and no heckling. So this is our roof plan showing our primary mechanical systems. You'll see we have shown in pink a centralized VRF system for our heating and cooling for the building. The purple is 4 centralized ERVs, and that's required for the ventilation for the building. This is different from what we often do for multifamily projects, where each unit might have its own dedicated heat pump and ERV instead of centralized systems that serve the whole building. The green equipment was a surprise system that we had to add for the compounding pharmacy. This is a dedicated air handling unit which provides both the space conditioning and the ventilation to the compounding pharmacy. The reason we found out about it sort of late in the design had to do with those two different timelines that Lauren talked about. So it really is not ideal to have those two different timelines, and it's something that you have to work through carefully. We found out that this air handling unit has to actually, it's a bit of a workhorse. And for health and safety reasons, the pharmaceutical code requires compounding pharmacies to be exhausted at extremely high rates. That was problematic for energy use, and I'll go into that a little bit more in just a minute. The last system that you'll see here on the roof was an 87 kilowatt photovoltaic array on the southern side of the roof, shown in blue. Here is a section view of our building, and you can see the heating and cooling is provided in pink there by the VRF system for most of the building, but for the pharmacy, it has its own dedicated air handling unit. Then if we look at ventilation, comparing the three typologies again that Lauren looked at in the last section, you can see the amount of ventilation required varies a lot. For a single family, you might have a ventilation rate somewhere in the range of 0.06 CFM per square foot, whereas a multifamily would be about 30% higher than that. Meanwhile, for the medical office building, it's about 4 to 5 times that of single family rates. It's interesting to note, though, that even though it's 4 to 5 times higher than a single family building, this doesn't actually qualify as a high ventilation building under the Massachusetts Energy Code pathways. High ventilation buildings, such as hospitals and labs, are ventilated at rates above 0.5 CFM per square foot. Figuring out if you're a high ventilation building is a critical issue for both energy usage and project compliance with Phius targets. So that was one of the first things we had to look at the beginning of the project. Here's a ventilation diagram comparing the amount of ventilation provided by the ERVs to the amount provided by the pharmacy air handling unit. The ERVs are about 87% efficient, whereas the pharmacy AHU is only around 50% efficient. Because of the chemicals being compounded in that pharmacy, the pharmacy has to be exhausted at 3 times the code required rate of other spaces, and it has to run all the time. So from an energy perspective, this was a big hit to the project. To keep our source energy under the Phius limit, we had to find a way to offset it. Turning down the ventilation to the rest of the building during office hours was a big help. So on nights and weekends, the ERV system turns down 50% to save energy. In order to throttle down the system for the ERVs after hours, we used special smart dampers called react dampers. Those can be individually controlled. That resulted in a 26% reduction to the heating demand for the building as a whole. But to give you an idea of just how much the pharmacy ventilation affected things, if you take that pharmacy AHU out of the equation and just isolate the 4 ERVs, turning down that system after hours would reduce the heating demand by more than 50%. Another challenge we faced near the end of design was med gas exhaust. Per Phius, building ventilation or the intake air and exhaust air must be balanced to within 10% of each other. So the challenge with medical gas storage rooms is that they are exhausted continuously, and that exhaust is not allowed to pass through the ERV system. So 1,000 CFM of air is being constantly exhausted from our medical gas room. And whereas normally in a passive house project, when you have an exhaust fan that's just being directly exhausted, like in a laundry room, you could bring in cold makeup air at that same rate, 1,000 CFM, and also bypass the ERV. So your ERV stays balanced. But in this case, we couldn't bring in that volume of cold air. It was just too much, and it would have made the space really cold and uncomfortable. So instead, we are bringing 1,000 CFM of makeup air through the ERV in order to preheat it. Using the ERV for intake air but not exhaust air is causing the ERV to be unbalanced at 7%. That's just the ERV that's serving this area. So the building as a whole is positively balanced to within 1 to 2%. That's under the Phius limit of 10%. We're feeling pretty good about it, but we're going to have to watch it during construction. Moving on now, I'll discuss the 5 Phius compliance targets and source energy in particular. I'll start by showing how we made out with our overall compliance targets. You need to comply with these 5 limits in order to meet passive house. You can see that we managed to obliterate our heating and cooling demands. We came in well below the limit. We also met the heating load fairly easily. It started getting closer to the limit for cooling load, but we were still okay. It was the source energy that posed the biggest challenge for us. We ended up just squeaking under the limit after a lot of, I think, tossing and turning and a lot of trouble. So I'll go through that process of how we finally got to passing on the next few slides. Just a quick overview of what source energy means. The electricity that our buildings use today is not necessarily from clean sources yet, and Phius wants you to take that into account. So source energy is the energy your building uses, which is known as site energy, multiplied by 1.8 times to account for the dirtiness of the average electricity production and distribution to the site. Renewable energy is helping green the grid, which in turn helps all buildings get closer to net zero. And that's why it's critical now that we design all electric buildings and significantly reduce our heating demand so that there are fewer carbon emissions and less demand on the grid. As mentioned previously, source energy is calculated differently for commercial buildings than for residential. Residential is calculated per person, but commercial is per square foot. And Phius gives a source energy limit of 24.5 kBTUs per square foot per year for commercial buildings. This is just a baseline starting point. So like Lauren said, Phius gives you an allowance for process loads that are required by code, like the compounding pharmacy, or due to your particular building type, like MRIs. What she didn't mention is that the design team had a heart attack before we knew about those allowances. So we saw initial energy modeling coming in at around 66, which was more than double the 24.5 limit. But Phius was great too. I highly recommend reaching out to them early in the process because they will work through challenges with you. And they let us total up the process loads, which came to about 20.5 kBTUs per square foot per year. And we added that to our baseline limit. The same thing occurred for the pharmacy ventilation. They gave us 10.7 allowance to account for that. So when we added both of those allowances in, our final source energy limit came to 55.7 kBTUs per square foot per year, more than double the starting point. However, It turned out that even with those allowances, we still couldn't quite meet the target. We had to dig a little bit deeper into our toolbox. The first thing that we did was add that PV that you saw on the roof. We added as much as we could, and that brought our source energy down the amount shown in blue there. So we came down from around maybe 64 to 58. It was closer, but not quite there. It was only after reducing the ventilation after hours from the ERVs, bringing us down the amount shown in yellow, that we finally squeaked under that limit of 55.7 kBTUs per square foot per year. With that, I will turn it back to Lauren to summarize things and talk about cost savings.
Thanks, Kristen. I'm going to close out with both lessons learned and with some potential energy cost savings. The first big lesson relates to separate timelines. As you've seen, MEP coordination is critical, and we really needed to contract MEP for tenant fit out earlier in the process. The next one is exterior wall insulation. I think due to the separate timelines, the initial internal and process load estimates locked in envelope decisions pretty early on. So smaller heating demand confirmed in the later tenant fit out CD phase actually revealed we could have reduced the continuous exterior insulation slightly below 4 inches. So that was a good lesson there. As Kristen mentioned, ventilation redundancy is essential in medical office buildings. Originally, we wanted one ERV per floor, a very simple way of reducing ventilation flow rates after hours. This allows the building to remain balanced. However, this would have risked full floor impact if one of the ERVs is down and needs to be serviced. So instead, for resiliency, we have all ERVs connected to every floor and use the dampers, as Kristen mentioned, to turn down the ventilation 50% after hours. So there's a bit of push and pull of balancing these things when we're looking at all these factors. Speaking of balance, unbalanced ventilation was a surprise that came up in the tenant fit out phase when coordinating the med gas ventilation and final calculations. As Kristen mentioned, Phius allows us to be up to 10% out of balance for the ventilation, and in design, we're at 7% for one of the ERBs. So something that we really have flagged and are we're following pretty closely in construction with the entire project team. Finally, early dialogue with Phius was so key. I think engaging Phius at the beginning of the project, specifically on the source energy limit, helped really align design decisions and avoid costly rework, contributing significantly to the project's success. So here we're highlighting another lesson learned. This one's actually pretty funny. It's not a pig or a person with a tail. It's the coordination challenge of installing an MRI machine, which is what you see covered in pink right there. Typically, blower door testing is done once the facade is complete. However, the facade will be finished before the MRI is delivered, which complicates things. To address this, we've designed a removable facade panel that will be removed during the MRI installation and then reinstalled and sealed prior to the whole building blower door testing. Another just coordination challenge. So before I go into the Massachusetts incentives on the next slide, I know Keegan highlighted this, but we thought it would be nice to just do a quick comparison between the Connecticut incentives to the Energize C2 program, which has both commercial and residential incentives. And, on the next slide, I'll go into Massachusetts. But it's just interesting to see. It's great to see that Energize Connecticut has the various paths under the commercial incentives. And under Path 1, which is the most aggressive or, you know,
Chris?
pathway, you can get up to $4 a square foot if the construction and post-occupancy energy use intensities are met. Plus, there's technical assistance available. And then there are many incentives for air source heat pumps, variable refrigerant flow systems, and ground source heat pumps. And then finally, with the residential incentives, as Keegan mentioned, there's the all electric tiers as well as the heat pump adder and the high performance certification incentive. So here's the Massachusetts incentives. As I get into the incentives and costs for the medical office building, I want to preface that this section is focused on estimated cost savings with the understanding that the building is in construction and some of the incentives will be realized with post occupancy. So here we're looking at both state and federal incentive opportunities. Under Mass Save, which we engage with them in schematic design, we pursued that Path 1 incentives, which focuses on that low predicted energy use intensity. So we can get up to $2 a square foot at the end of construction for getting below the established EUI targets. And then we can get another $1.50 per square foot in post occupancy if, again, we're below that EUI target. So we can get up to $455,000. Then with the heat pump incentives, we have a combination of both air source heat pumps and VRFs, so we can get up to $250,000. And then through the Inflation Reduction Act, which is not dead, it's still there, we're going for the 30% solar panel incentive under Section 48E. So we've looked into safe harboring the solar panels, meaning putting down a payment of 5 to 10% the cost of the PV, which allows the project to secure the incentive before the program is phased out. So here we're looking at estimated energy costs per year savings compared to a baseline. The baseline and proposed energy analysis were done through the Mass Save process. So comparing the proposed project to an ICC 2021 baseline, there's potential energy cost savings of 20 to 30%, which increases to 25 to 35% with the on-site PV. And then finally, in summary, we have $135,000 of savings for doing double glaze in lieu of triple glaze windows. We have up to $845,000 for state and federal incentives. We have a 30% peak heating reduction, which translates into smaller heating system. And we also eliminated the need for perimeter heating, which is an additional cost. And then finally, we have 1.5 to 2 million potential energy cost savings over 20 years based on the current electricity rate. So thank you. That's a wrap. We'll now open it up for questions.
Hi, thank you, Lauren and Kristen. We have one question so far, excuse me, in the chat, which is from Melissa. I'm surprised Passive House doesn't just deal with the core and shell. What if the tenant changes?
Yeah, so in our code, I mean, that's a great point. In our code, so we are required for the core and shell to do the Passive House pathway, and then the tenant fit out is also required to then do the Passive House pathway. We decided that it was more advantageous from, I think, from a drawing standpoint to go in with the same building permit under core and shell and tenant fit out and show, instead of showing a continuation of trying to do two Passive House pathways. I don't know, Kristen, if you have anything to add to that.
Yeah, you do have the option of doing, if you're doing a fit out later, you can do your own Passive House process and you have to show continuity with the previous design and Passive House methods. So we were able to get our schedules aligned enough that we were able to do it as one project, which I think was simpler, but it is interior fit outs don't get a pass. They also have to meet the energy codes.
And Phius was very, they really wanted us to provide that energy use for that fourth floor that is vacant. They wouldn't allow us to just submit it as empty as part of the Phius certification, which is also another aspect when dealing with this kind of empty spaces.
Where was the ventilation
Yeah, so
ramped
the
down after
question for
hours?
anybody who can't see it is where was the ventilation ramped down after hours?
So it was ramped down throughout the whole building except for the compounding pharmacy. We had to keep that going 24/7.
Yep. So basically, it relates to the unoccupied spaces, which is and the non-critical
Yeah.
areas.
Would you guys say this was one of the more challenging or more unique projects you've worked on?
Yes.
Def- Definitely. It
Yeah.
was, we felt like we were creating the wheel a little bit.
Yeah.
Yeah.
But the best thing was how much Phius worked with us whenever we had challenges that seemed insurmountable. I think they really support the process and want to help you get there. And we do, in order to get our final certificate of occupancy, we do have to be certified. Um, if you fail to get your FIA certification, I believe there is a workaround, but they've made it very onerous.
Yeah.
It's
You
not
can,
recommended.
yeah. You can fail by a certain percentage for the air leakage testing and believe the duct leakage, but you have to make every, last resort, effort to really pass. Um,
That's right. And one of the biggest challenges with buildings like this, where you have centralized ERV systems and you've got sort of tall shafts going through the building, is getting things balanced.
yeah.
It's apparently quite difficult. I mean, it kind of depends on what passive house raters you talk to, but I'm doing a couple of multifamily projects right now, and our rater has very much argued for us to not do centralized systems. He wants us to put a separate ERV in each unit, even though it means going out and penetrating the building facade, 300 times, right, for each unit. He still prefers that to being able to get your FIA certification.
Yeah, this project has car dampers, which are critical to that balancing. Stephen Winters has been leading the charge on this in terms of the balancing large centralized systems. So we got that early in the design. And then on top of it, we have the React dampers, which is what really throttles down the system to by 50% after hours. So it's definitely a heavy duty, tech technological building.
Yeah, yeah. And your mechanical engineers have to really get engaged
Yeah.
more than they're used to, I would say.
Um, was the pharmacy AHU on a heat pump? I've had trouble making heat pumps work for very high ventilation loads.
Yeah, it wasn't. It was its own air handling system. Yeah.
It wasn't gas.
We don't have any gas to this building. The owner was shocked.
Yeah, it's one of it's we'd have to clarify exactly what was supplying that air handling units.
But it was electric.
It was electric. Um
Here, Melissa, I'm gonna let you, because Melissa, yeah, you have good questions. You can get the dialogue
Yeah,
going.
I was just wondering because you didn't have to count the energy used for the AHU for your analysis. So I'm just wondering how big a load that ended up being. I'm assuming it's a heat pump that's providing the heating and cooling for that AHU. But I was just curious. Well, I don't with probably an electric resistance backup. And I'm just, we've kind of tried to stray away from that just because of the high energy costs associated with the electric resistance.
Yeah.
especially if it's a really high ventilation load.
That's a good question. If we had our mechanical engineer, I'm sure he could answer that. But we could follow up with you
Yeah.
later and get you an answer.
Yeah, I would be curious to know what ventilation system you used for that
Okay.
pharmacy.
Yeah, we weren't quite involved with that on the tenant fit out side. That was more the tenant fit out architect.
Yeah.
That was something that came up sort of late in the tenant fit out design. But one thing I can clarify is that the heating demand with the pharmacy is 3.25, and then the heating demand without that pharmacy is 0.45. So a pharmacy is a significant part of,
Huge. Yeah.
yeah.
My one other question is about hot water. I'm wondering what your solution was for hot water.
Yeah, we had centralized hot water heat pumps as well up in the mechanical penthouse.
Great, thank you so much. That's a very interesting project.
Thanks.
Thank you.
Thank you.
Well, while we do maybe a last call for questions, Sarah, do you want to just do a reminder as far as folks interested in CEUs?
Sure. For AIA, Build Green CT will be submitting for you, and hopefully you included your numbers when you registered. And that also includes if you want a certificate. Hopefully you indicated that when you registered. And in our follow-up email, we will include instructions on how to self-report for Phius.
Great. And I'll just plug, it's not officially scheduled or, well, it's not announced yet, but we will have another Passive House specific session coming up in July looking at affordable multifamily housing using the Passive House standard. So keep an eye out for that. But not seeing any other questions, I think we can wrap for today right here at 1 o'clock. Lauren and Kristen, thank you so much for joining. This was a really interesting and engaging presentation, and we appreciate your time.
Thank you.
Thank you for having us.
Yeah,
Yeah.
thanks to the sponsors of Energize Connecticut, and keep an eye out for announcements for future sessions.
Thank you.
And thanks to you, Sarah.
Okay, thanks. Bye-bye.
Take care.
Bye.
Bye.